Hey guys, we are Hong Long Long Hong Hong Kong 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 Long Chong Chong Chong, and our leader is Hong Hanlei, and I'm Ye Mia, and another member is Lai Jiaxing, and this is our progress presentation. So the first thing is specifications. We do the two different module this time. The first one is we use two 128 bits register to store both inputs value and the output value. And the second one is the method that we talked about before, that in the concept presentation, we only store the output value. So we only use one of 128 bits register. So you can see that the timing, the first one is much more slower than the second one. And the score, the first one now is all correct. And the second one now, we only do 80% correct. So we're still working on it. And for cell area, the first one, it used 4,436 gig count, and the second one we use 2,159 gig counts. So the cell area has decreased to less than half that we use the second method. And this is our implementation method. So how do we updating data in flip-flop? What if the actually smaller one has larger value in the middle round of the comparison? Will the value stored in flip-flop become not A nor B? So we use FSM to control the state. For example, for maximum, at first it will stay at the undefined state. If it is equal, it will stuck at undefined state. And if it is bigger, then it will jump to the accept state and stuck at this state until the round end, and it will back to undefined state. And if it is smaller, then it will go to the discard state and also stuck at this state until the round end. And this is our comparison. You can see that, like we just see, the first one, the data arrival time is much smaller than the second one, but the area and the power are both smaller. The second one is both smaller than the first one. And this is our system architecture, and this is our circuit diagram. So at first we have the counter to that have 7 bits, which the last 4 bits represent the cycle number, and the first 3 bits represent the round number. Because when the counter counts what number of a cycle is, it will count like for 0, 1, 2, 3, and until 16, it will have a carry 1 to the round, to the fifth bits, so the round will add 1. So we take the first 3 bits as the round number and the last 4 bits as the cycle number. And we also have the comparator, which will compare the IoT in value and the IoT out value, which we previously stored, and it will output it is bigger or equal to the change. The change is a module that change the output register and to whether it will write the new number or not. And the counter and the change will go into decoder and then RF to tell that RF that it will tell DL to be clean value or IoT in, and it is controlled by the change output value and the decoder output value, that it will tell that which part of the output memory we are writing now. And then the R16 RF will go to the MUX 16 to 1. And then for shift module, we have IoT in and the cycle number. Then it will output the true value of IoT in, because shift module is that transfer IoT in 8 bits to its true value of IoT 128 bits. So it will tell the adder what is the true value of the IoT in. So the adder will add the output with inputs, then it will rewrite the output again. And this is our circuit diagram, which we synthesize it. And the next one is known issue and the subject to be learned. So for known issues, the first thing is the chain to module is hard to design and integrate. And the second one is the timing of counter register change and value. That is, if we don't actually know that counter register change and value will synchronize. And to be learned part, the first one is FSM design for a more clear view of timing. And the next one is we want to have a better adder because for now we only use C equal to A plus 1. We don't use others module different adders. And the next one is reference. From TA, we know that extract and exclude can use KMap and flip-flop detector. For example, for extract mode, if the pattern equal to A and then all F and then last one is 0, 0, it will, if we only detect the first first 8 bits to be A, then it will be correct because this pattern is in the range of extract. But if we use the same method to see the first 8 bits is A or not, then you can see that the second pattern, if it is A and then all F, this pattern, the first 8 bits is also A, but this is not in the range of the extract because it is equal but not smaller. So we use FSM to detect this corner case. So at first, it is all flip-flop, and if it is flip-flop, it will stay at the all flip-flop. If it is the input isn't flip-flop, it will go to the not all flip-flop and stuck at this mode until the pattern is down. So this means that it will detect all the inputs. If it is all flip-flop, it will stay at all flip-flop. But if one of it is not flip-flop, it will go to the not all flip-flop. And the next reference is from Hakuna Matata that an efficient 131 bits adder from IEEE Explorer. So because we haven't write the adder submodule yet, so now we simply use assign C equal to A plus 1. So we want to use another efficient adder. The second one is progress and simplified result. So for the version 1, the area timing power is shown at above. And the second one, also the area timing power is shown below. And you can see that the timing and power is much smaller than the first one. And the next one is pending task. The first task is we want to reduce critical path. Now we have small area, but so we aim to speed up the circuits. The second one is better coding style. So we may use a spyglass and coverage and maybe DFT. And the last one is function correctness. We will debugging and integrating with adder. Next one is text division. So I'm in charge of integrating some module and progress reports and also synthesizing. And Hong Hong Ling is responsible for submodule writing, optimizing design, and the final report. And Lai Jiaxing is in charge of simulation, synthesizing, and progress report. And for our work schedule in Gantt chart, so the green one is the Gantt chart that we already done. The blue one is the part that we haven't done. And the pink one that design a better one, that is the new schedule that we add on it because we want to design a better one module. So it will be at this week and the next week we'll synthesize it. And so this is our progress presentation. Thanks.